Hello, Energy Physics here with the third in a lecture series on our quantum and quantum field theory, quantum gravity, and Newtonian physics lectures. These lectures are essentially complementary background information on the quantum and gravity and Newtonian physics books that I wrote and published between 2012 and 2017 or so. They're all available on Amazon.com, Hatcher, under How to Succeed at Understanding Newtonian Physics, How to Succeed at Understanding Quantum Field Theory, and How to Succeed at Understanding Quantum Gravity. If you're interested in a more detailed explanation or discussion than I'm providing in these lecture series. So this particular lecture, being the third one, is about Newtonian physics, but looked at from the perspective of Planck scale quantum theory. Some very interesting results can be looked into from the perspective of the theories that I've developed over since 2012 on particle theories that form the basis of quantum field theory, quantum standard model, and how those map to Newtonian physics concepts, where we can actually calculate the number of photons and the number of mass quantum that are in these various Newtonian physics behaviors. And this is known as the equivalence principle when it comes to gravity and slipped my mind here. The equivalence principle and the I'll have to think of it. The same equivalence principle from the Copenhagen interpretation that begins with a C. I just can't remember it right now. So let's get into this discussion on Newtonian physics and start the slideshow from the beginning. We talked about previously where the photon and the quark are the two most important fundamental particles in the universe. And we've added to that the concept that the quarks themselves are also composed of composite. We haven't been able to break these apart yet, but we're theorizing at the Planck scale that the photon quantum has a complementary mass quantum that is identical in behavior other than particle properties. And these two photon and mass quantum interactions form all the basic particles of the standard model: the neutron, the neutrino, the electron, and the proton that are stable particles. And composites of those also form the other particles that are created in particle accelerators. They're just different levels of complexity of how these two particles interact and what kind of composite structures they build through the interaction of gravity and force inertia, which operates at a very, very small scale down at the Planck scale. So it's got very, very large energies and very, very large forces to bind these particles together. And the principle of motion, inertia, and momentum changes are that these particles basically collide down at that level, and they impart their small changes in velocity and small changes in inertia and acceleration based on the numerical balance of all the particles, the free state particles in the universe called dark matter, also the same particles forming the dark energy expansion concept, where the particle balance is essentially imbalanced on one side and there's less of those particles impacting on the other side, causing motion and inertia. And if the halo is homogeneous all around with no screening densities caused by bound state mass quantum, which are fermions, and free state mass quantum, as long as those forces are balanced, we'll get zero gravity. When they're not balanced, we'll get gravity in the direction of the screening center of mass, whatever that happens to be, whether it's an asteroid or a center of a nucleus. So these things are driven by collision, absorption, and emission theory that we're proposing in these lecture series, CAE type phenomena. So the key is you have to map the equivalence principle and the correspondence principle. That's what I was searching for, coming out of the Copenhagen interpretation of quantum field theory, and that has to map up and be equivalent to the observed Newtonian physics without violating any Newtonian physics behavior. So our model does that. We're able to calculate energy levels, which are primarily energy Lagrangians that supersum up into the Newtonian type of energy Lagrangians, which are the basis of Newton's force. Force equals mass times acceleration, and then energy levels in the energy Lagrangian, 1/2 mass times velocity squared. Then you get minus rho gh, which is the potential energy added to that, and then you've got other types of Lagrangians, spring constants, and other types of forces like friction that you make equal to the left side of the equation, which happens to be Planck's formula that we've extended to gravity. And so Planck's energy levels, the Lagrangian energy levels, are the sum of all the energies of the particles interacting is equal to the sum of all of the h dot Planck constant times the frequency, which in this case is the angular spin velocity of the photon quantum, and that's a discrete quantized level, a quantized energy level that only has one specific value for every energy as it comes out of the electron or out of the proton, and it's released as a free state. And then the same property occurs with the mass quantum, where that sum of the energies is equal to the sum of h bar times the frequency, nu, plus or minus g dot, which is the gravitational equivalent of Planck's constant, and times omega, which is the angular spin velocity of the mass quantum particle. And this particle is much, much smaller in size than the photon quantum. We're estimating it to be somewhere around 10 to the minus 55 kilograms in mass, and somewhere around 10 to the minus 70, 75 in terms of 10 to the minus 75 meters in size, which is incredibly small, much, much smaller than the Planck scale particles. So the basic lecture is the goal of this class to understand the universe of the physics by understanding how these two particles interact to create all the conventional and observable Newtonian physics. And that's a concept of measuring human size scale observables, which are often composite illusions of reality, especially at the Planck scale. We can't actually see the quantum interaction other than interference patterns that are common when we do different diffraction gratings or some other index of refraction where special relativities it takes effect as the photon quantum travels from electron event to electron event and simply travels a longer distance and has different scattering angles the more dense the material is. And that longer distance gives us the illusion or the impression that the photon is actually slowing down, but it does not. It travels at the same speed of light always between the events. It just travels a longer distance. And that's true of traveling through two different types of materials, index of refraction type concepts, as well as the photoelectric effect that was explained by Albert Einstein, where these photons basically knock out one particle and disturb a particle, electron or a proton, and create electron flow, which flows down a wire. And those electrons don't actually move down that wire, they just vibrate from state to state and from molecule to molecule, while it's the photon that travels the speed of light down that wire. This is a concept that's not well understood even by some physics that are teaching physics in college. So we'll move on to this basic concept of human observables versus non-observables. Humans measure everything in relative space. Only the particles themselves know what absolute space is. And our human observables require delays due to special relativity in the measurements. We always are looking backwards in the past to an event that takes time to actually arrive at our detector. And we can only measure what happens now in the detector, and we can never measure simultaneous events. So this basic concepts of quantum entanglement and quantum simultaneity basically are false representations, and we need to think of particle physics and even Newtonian physics as a particle-based theory that involves finite states and finite sizes and finite observables. Nothing is zero and nothing is infinite, which is where we get into trouble with quantum field theory equations and field equations, where they drive to infinity to values that are not actually true in real physics. So here we got units of measurement on the left-hand side that are common. I'll let you take a look at that. Force being one of the most common that we use in Newtonian physics. The other, more important, is energy, which is in joules or Newton seconds, Newton meters. Actually, force times the distance will give you energy. And that's equivalent to h dot omega, which is the summation I described previously, plus the gravity component of g dot omega, which is the angular spin velocity of the particle. For this concept, we don't need waves. In fact, we prohibit it. We don't need wavelengths. All the expressions are done in frequency, and they result in exactly the same energy levels that you get when you look at the spectrum of light. All the different colors can be described that way with the same numbers, just looking at it from a different perspective in terms of water waves and water particles. So we prohibit waves, don't use wavelength, and we only use frequency as the angular spin velocity of the particle. The mass quantum and the photon quantum always travel at the speed of light in a linear direction, c. So we've got different scales that we're looking at in this lecture. The basis of Planck scale theory has to map upward through the quantum nuclear scale and not have any surprises or descriptions that don't match the current acceptable theory or observations. And these theories we have mapped perfectly into that as energy Lagrangians, because all the quantum field equations are also energy Lagrangians, and we can equate those on both sides because energy equals energy. We just supersum all of the Lagrangian energy levels of small particle interactions until they match the exact same energy calculations done with the quantum statistics or with the Newtonian scale of Lagrangians that are calculated using the classical Lagrangian concepts of kinetic energy and potential energy. The equivalence principle is used for gravity. Again, we have to map in from the Newtonian scale. Does not and cannot violate the quantum scale, and the Planck scale cannot violate the quantum scale or the Newtonian scale. So all of our mathematics is based on fitting into that concept without invalidating any current observables or invalidating any current theories. We're just creating a different way to do the calculations and the numbers and look at it from different descriptions of reality. So what is a photon? We've already talked about that in previous lectures. We're going to use this concept again in Newtonian physics, where we have the particles, quantum mass quantum and photon quantum, doing all the interaction and all the force carrying, and we call that anti-space with some fixed radius, which is size unknown, and somewhere to 10 to the minus 75 meters is what we've estimated the size of the mass quantum. That has an angular spin velocity omega, and we can calculate that with n times omega, and we can even superimpose and get what look like waves when in reality it's just a spinning particle. It either spins in the direction it's traveling, or it spins in the opposite direction of its travel, based on the same concept of photons measured in quantum field theory. They can only spin in two directions, and they're polarized, either positive or negative spin directions. Newtonian physics is, again, an approximate science of human observed motions, and those are motions of bound state mass quantum groups that are known as fermions, or particles with mass, and their average observable interactions with photons and any undetected particles, which cause gravity. Those particles are at mass quantum according to our postulated theory. In Newtonian physics, you basically have measures of inertia and measures of momentum, where you're estimating the average velocities over a measurable distance that you as an observer calculate from a relative phenomenon, understanding that special relativity applies anytime these particles are moving close to the speed of light, and it takes a finite amount of time for the information to come from the past to the present when you measure a time interval from time 1 to time 2. The T1 is in the past, T2 is the current sensor measurement, and we can pretty much ignore that when it comes to Newtonian theory. Becomes a real issue when these particles are traveling close to the speed of light, and we have to make that correction because it's a composite illusion that we cannot accurately represent the original origins of the event because it's delayed in time, and the photon quantum and mass quantum travel a longer distance to get to us based on what they interact with and how dense the particles are they have to interact with from T1 to T2. Basically, this is the basis of foundation of velocity, and from this we then move to acceleration curves, again factoring over time intervals. Newton invented the differential calculus to describe observed motions of acceleration, where the acceleration is a constant. He actually didn't use any of these algebraic formulations. He used geometry. The radius r vectors and r plus differential r are pretty much similar, only in his derivations in the Principia, they're all done with geometric proofs. So it's quite ingenious the way he arrived at the same types of velocity and acceleration concepts and acceleration across an arc over small angles. Modern physics use acceleration as a constant typically when we're calculating Newtonian physics, which is Newton's first law of force equals mass times acceleration. And it's not Newton's first law, I'm sorry about that. The basic concept is that you've got a force and it's equivalent to all the summation of the masses times the acceleration of all the masses, and that's the sum of the forces, very superposition type of a principle. And then we can calculate velocity as differential distance s over a differential time t plus an initial velocity, and the distance traveled, if we do that as an integration, would be 1/2 the acceleration times the time squared plus the velocity times time plus an initial distance starting point s from a reference frame, relative reference frame. And again, that equation is a trajectory type of equation that's used in ballistics equations where we're not, forces are not interacting simultaneously or continuously through the particle. Newton's contemporary, Christian Huygens, added another concept when he studied angular motion and pendulums, and that is the angular acceleration and angular velocity. Angular velocity is omega, which is the rotation it goes through over time, angle rotation divided by the time that it's involved. And this follows from Kepler and Copernicus' basic laws in sweeping out equal areas equal times kind of concepts. Christian Huygens extended that concept to the angular velocity. Omega is equal to the angle that it sweeps through divided by time, and then the acceleration is the angular velocity, tangential velocity squared divided by. I need to reverse this back so you get back to that slide. Still keep talking. And the angular motion is the acceleration is the velocity squared divided by the radius r, and assuming small angles. Vector calculus was invented to approximately describe motions as vectors. A lot of Newtonian physics is analyzed using geometric vectors. The concept of vectors being a magnitude or a unit quantity times some amplitude and a direction in terms of a 360 degrees from a zero reference. So we quite often end up resolving those angles in direction cosines multiplied by a magnitude. So you get alpha times direction cosine of theta is how we basically find these distances that we then sum up in x, y, and z directions typically. We describe a coordinate system as Pythagorean rules we quite often use of triangles add, subtract, and these vectors, while we do cross product matrix rule calculations are used to multiply and divide these vectors. There's quite a bit of mathematics involved in cross-product multiplication. Vectors are added head to tail, and then you have basically a resolution or a summation of all of those that give final magnitude and final direction. Newtonian physics is all about measuring the average velocities and the average positions over times to get velocities, and we measure the average changes in velocity to get acceleration. Again, velocity is equal to distance divided by time, and acceleration is equal to velocity divided by time. And you get two other equations other than the distance equation, where you're looking at the differential position is equal to the 1/2 acceleration times time squared plus velocity times t, and that's initial velocity, again, velocity of x. And another useful equation, velocity squared final minus velocity squared initial is equal to 2 times the acceleration times x. And these are typical, again, ballistics equations used quite often in college physics courses. And you plot those using Excel as a useful tool to look at various accelerations over time and positions over time to get velocity and velocities over time to get acceleration curves. The average velocity giving you acceleration, and average acceleration giving you changes in acceleration, basically. Vector components have relative positions, as we described before, over time. So quite often these vectors are done with calculating fields, and fields are used often in Newtonian physics, not to complicate things, but these are not normally tensor fields, they're usually vector fields, and useful in terms of calculating various types of parameters that have amplitudes distributed over a large space, whether it's the surface of a sphere or a flat plane or some type of a change in gradient where the field changes as a differential increment from field location to field location. And don't really like the use of fields that much because it's a virtual concept where the center of the field is 0 until you multiply it by some amplitude. But the mathematics of it is usually differential or divergence type calculations, sink and source concepts used very often in analyzing magnetic fields and electric fields created by the photon and by the mission and travel of photons from electron to electron and through wires and through antennas and various Newtonian level type devices. You got relative velocities and relative accelerations that you can calculate. Again, Excel is a useful tool for doing these for various types of Newtonian problems. Huygens does most of the circuit motion and pendulum analysis for Newtonian type physics. Usually it's done with small angles that approach 0, where the sine of theta is equal to theta in a small angle, almost close to being equal to theta. And the arc distance s is equal to r times theta, which is the same as differential velocity over average velocity times the radius r. And that's Christian Huygens equation, where you end up with centripetal acceleration, which is the opposite of centrifugal acceleration. And that acceleration on the tangent is a differential velocity or the differential omega. Depends on whether it's an angular acceleration and angular velocity, or it's a linear acceleration and a linear velocity. So you have two separate concepts. You have a tangential velocity vt that's calculatable, where the acceleration for that is vt squared over r, and then you have vt itself being 2 pi r divided by the period, which is represented by t, how many cycles per second you have. And then omega is your angular velocity, and radians per second is the angle theta that it travels through divided by the time measured. And then your frequency becomes omega over 2 pi cycles per second, the period t being 1 over frequency, And these are basically used in Newtonian physics calculation of Huygens experiments. Orbital motion can use some of the same equations, however, remember that gravity has a value that was determined by Newton's constants and Newton's formulas, or the gravitational constant, to arrive at what is the acceleration of gravity, and it's measurable today as 9.807 meters per second squared, using the radius of the Earth of 6.38 times 10 to the 6 meters, and the tangential velocity is gravity times the radius to the 1/2 power, which can do a rough calculation of what speed's needed to put a satellite into a circular orbit, and that velocity is 9.807 meters per second times 6.38 times 10 to the 6 meters, which is the radius of the Earth, to the 1/2 power, and that's your velocity, 7,910 meters per second will put a satellite into a circular orbit around the Earth. Simple calculations, not really the complex calculations used by spaceships and orbital transfers. Those are a little bit more complex. Pendulum motion, again, was investigated by Christian Huygens. It is a Newtonian level physics for small angles again, and we basically have the arc of that pendulum is equal to the radius times the theta, the angle it moves through, again with small angle approximations. R times sine of theta becomes equal to R times sine omega t, which is the angular velocity times the time, which is its measured time. Frequency is 360 divided by 2 pi omega in terms of cycles per second, and the period is 1 over the frequency in terms of second, and with a wavelength. Lambda is equal to the tangential velocity times the force times the mass is equal to 4s. It's another common equation that he's derived. Theta is omega t in radians. Accelerations, so tangential is gravity times the sine of omega t. You've got omega is equal to g over r to 1/2 power. Period is equal to 2 pi radius divided by gravity to the 1/2. The period is independent of the mass, is something that Huygens discovered. And of course, the diagram on the right shows the tangential difference between tangential accelerations equal to g times sine theta, and the radial acceleration is g times cosine theta, whereas g is a vector straight to the center of that radius at 9.80 meters per second at the surface of the Earth. It's less than that above the Earth and less than that below the surface. Maximum gravity is always at the surface of the planet, and it's 0 in the middle and 0 at some distance out in space. Remember that concept. Again, a simple question would be on a physics test in college: what radius is required to get a pendulum clock to tick at 1 second? You basically measure that radius as r is equal to g times the period divided by 2 pi squared. So that becomes 9.807, which is a value for g, times 1 second over 2 pi, which is the period, and you square that, and you get basically a radius of 0.248 meters, or 24.84 centimeters, required to get a pendulum clock to tick every 1 second. So that's quite a distance, and that's why most pendulum clocks have really long pendulum arms on them, typically at 24.84 centimeters, 0.2 meters. So we have this statement that the problem with understanding modern physics is that most of these Newtonian approximations are an illusion of real Planck scale size particle interactions. In other words, we can't see the zigzagging back and forth of all these particles. Our observations look smooth, but the actual movement is a result of photon quantum impacting electrons and changing their delta momentum and changing their inertia in zigzag or staccato type pulses. These are a result of photon streams impacting the electrons and impacting the protons in the molecules of Newtonian scale devices and Newtonian scale objects. The same thing happens with us in terms of gravity, and the same thing happens with us when we're moved inside of an jet airplane, and we're pushed along by the photons pushing on the seat of our chair and pushing us through the sky in an airplane. All that is photons. So that's all doing. Photons are doing the pushing, and gravity, mass quantum are doing the pushing in terms of toward the center of the Earth. And our theory is going to show that that maps to Newtonian curvatures that are smoothed out because we can't see the actual quantum level interactions or the Planck scale interactions, which are events that happen over time in a pulse stream, as these interaction events are caused by large numbers of photon quantum interacting with large numbers of mass quantum in bound states or free states. Billions of events happen which create these Newtonian human scale observable illusions. They're composite illusions in time, generally delayed by special relativity. Anytime that you try to do a human measurement, again, I said only the particles know and understand absolute space, and only the particles can determine traveling at the speed of light, absolute value of c. Our knowledge of energy and time and position and momentum is limited by the Heisenberg uncertainty principle. If we could see those tiny little perturbations using a microscope, or could get down to measuring those vibrations, we would have energy and time that would not be precise. We could do precise time and non-precise energy, or a precise energy and a non-precise time. Same thing with position or momentum. We could get a precise momentum and a non-precise position, or a precise position and a non-precise momentum, due to Planck's constant and the Heisenberg uncertainty concept that humans have to deal with. Now, the particles themselves probably don't deal with Heisenberg uncertainty. They know exactly where they are in space at any time. They have a point momentum and they have a point velocity, and they pretty much go into a particle, absorbed as a collision, absorption and emission event, and they go from one state of momentum to another state in a capture state inside of the electron or inside of the protons. And then they get re-emitted at different energy levels if additional energy comes into the system and ejects them. So this is a basic concept of how Planck scale physics causes motions and inertias that we measure in the Newtonian world as what look like smooth accelerations and smooth velocity, constant velocities. And these are step functions. As we change that inertia every time a Planck scale mass quantum or a Planck scale photon quantum slams into an electron or slams into a proton in the molecule of our Newtonian scale object, we get these step functions and changes in velocity and inertia in a quantized way. And the inside, during the event, there's a slight acceleration as you step up to these constant momentums. And as you go through human time, there's more and more uncertainty in the path of these objects, because you're always looking backwards in time as a consequence of special relativity, and you can only measure the present event. You can't measure accurately the previous events of the past unless you've stored them and captured them in some type of a information capture device. We're going to blast through these equations. So here's our basic concepts of Newtonian force summations and energy Lagrangians that we want to talk about as the heart of this theory. There's always a bound state mass quantum or a fermion object that supersum energy levels in their bound state to equal the total of the mass and the total energy of the system, and that could be at rest or it could be moving. It just depends on whether there are gravity mass quantum interacting with it and colliding with it, or free state photon mass quantum interacting and colliding with it, that push it and move it and give it the Newtonian concept of force is equal to the mass of the object times acceleration. So the sum of the forces is always equal to mass times acceleration in Newtonian physics, and for every action there's an equal and opposite reaction caused by inertia. And basically these are Newton's laws. The first law being that an object, once placed in motion, remains in motion until acted upon either by photons or by mass quantum causing gravity. Some of the forces at the second law is the mass times acceleration, and that's a sum of all masses and accelerations in small particle theory. And for every action there's an equal and opposite reaction. That means if photon quantum push against the electrons push back, and that's what causes displacements and changes in motion of the objects in space. We use an energy Lagrangian instead of some of the forces because of the discrete energy levels, and we can equate that to Planck's constant. On the right-hand side of a Newtonian Lagrangian, it evolves to potential and kinetic energies. The kinetic energy is 1/2 the mass of the object times its velocity squared, minus the potential energy, which is a velocity as a function of radius, and we typically resolve that as the mass of the object times gravity times its height. That's the potential energy factor. And what we put on the left-hand side typically is the Planck's constant, and the Planck concept at the Planck scale that we also evaluated is a supersummation of energy Lagrangians, and that becomes the sum of all of the energies of all the particles interacting is h, the sum of h bar times frequency nu plus or minus g dot times the omega angular spin velocities. That's all on the left-hand side, and that basically determines the numbers of photon quantum on the left-hand side and the numbers of mass quantum on the left-hand side, super summed up to the same energy value that's calculated on the right-hand side. So this formula is useful for calculating the numbers of particles that cause these forces and cause these energy values on the right. And this is how we basically map Planck scale physics into Newtonian scale observables and phenomena. Galileo did a lot of studying with constant velocity and linear motion, primarily with inclined planes. He was the first to formulate rules of human observable motion on a scientific basis of evidence and experiment. He was followed by Isaac Newton, who depended heavily on his prior knowledge to study motion also and create the laws of inertia known as Newton's laws, which we just previously reviewed. And we just won't look through this, but energy is always done in terms of joules, which is Newton seconds. Newton meters. Newtons of force moving through a distance or a height creates an energy level. And this is also sometimes known as work, and we can get work displacement and energy concepts becoming equivalent, depending on our definition of what work is and our definition of what potential and kinetic energy is. Again, note at the Planck scale, we've derived that the sum of the energies is equal to the sum of h bar omega, which is the angular spin velocity of the photon quantum, and we leave out the gravity concept of g dot omega. We miss a small portion of gravity contribution to that, but we can create essentially a sum of the mass of the quantum particle times its length of interaction divided by the time of the interaction interval times the length of its value omega over the time interval of omega, which is the angular spin velocity. And so that's how we get mass times acceleration at the Planck scale, equivalent to h dot omega plus g dot omega concepts. All energy Lagrangian supersum to Newtonian and also supersum to quantum energy levels that we measure in particle accelerators. I don't need to talk too much about this particular information, just saying that all observables are relativistically corrected, primarily because we're looking at the past. And we talked about Cherenkov radiation before and why, as these particles approach the speed of light, when photon quantum are doing the pushing and particle accelerations, they emit Cherenkov radiation, which is photons in the blue spectrum. Whereas with gravity wells and blank stars, photons are not doing the pushing. It's the mass quantum and gravity that are doing the pushing, and as they approach the speed of light, it's the mass quantum that get released, and we don't see that. Those mass quantum are not measurable with current sensors. And this is a plea to all physicists out there, for God's sakes, stop teaching your students about elevator relativistic human analogies and train analogies and spaceship analogies they just aren't real, and it become imaginary fantasies that you can't actually execute. There's no way you can get an elevator and measure the speed of light before it goes way out past the scale of the elevator. So talk about these small particles and talk about particle accelerators, talk about photons interacting with masses and mass fermions and all that other stuff is real physics, and then map it into these Newtonian concepts of force and energy Lagrangians, and you'll be a better professor. Newton's second law can be summed over objects, where the sum of the forces is on the left-hand side, and then those individual forces are just summed in your individual components. The total of those become the total force on the object and causes it to move with its mass times acceleration. So you can calculate using its mass, you can calculate its acceleration if you've got a constant force interacting. Again, this is a static force diagram, so you can calculate what total force is needed to accelerate a 500 kilogram object at an acceleration of 6 meters per second. This is a common college level question. So you just sum the forces up is equal to mass times acceleration in kilogram meters per second squared. That's newtons, and that sum would be 500 kilograms or 6 meters times 6 meters per second squared. Gives you a force of 3,000 newtons that's required to accelerate a 500 kilogram object to 6 meters per second. Sum of the forces equal mass times acceleration. For every action, there's an equal and opposite reaction. Is basically these two forces oppose each other, and one force is positive, the other is negative, and you can balance those equations and get the combined acceleration of the system by accelerating. Acceleration is equal to 100 newtons by minus 40 newtons divided by 100 kilograms plus 200 kilograms. The summation of the bodies is equal to 0.2 meters per second, and that's a combined acceleration of these two masses interacting, one pushing against the other in an equal and opposite reaction to cause motion. Now you start to get into pressures, and pressures are a result of, again, molecules slamming into other molecules, and those are driven by photon quantum and mass quantum slamming into the molecules that are containing the electrons and the protons that mass quantum interact with for gravity, and photon quantum interact for force, photon force inertias. So we can call these pressures, and so 1 Pascal of pressure is equal to 1 Newton per meter squared, and we get 30 Pascal of kilopascals of forces. We can sum those forces using integral calculus across that pressure vessel. Force is basically divided by area, and that's where we get pressure. Pressure is a unit for pressure is a force per unit area concept, and it's measured in pascals in the MKS metric system. The equilibrium value of force 3 can be calculated, and the sum of the forces in equilibrium. Just go through that equation, and you get force 3 sine theta minus force 2 is equal to 0. Is equal to 17325 times the sine of 30 is equal to F2 is 86,602 newtons, and that's the equilibrium value of force value 3. I'm going to move on here. You got torques now, also as a Newtonian concept. All that is a force that's offset through a center of gravity will cause rotations. Those rotations are a result of torques. So they move through angles, and you can get angular velocities in terms of radians per second. You can get angular accelerations. In the Newtonians, the force times the distance, it's a distance arm or a lever arm, gives you the torque. Okay, so the force times the distance L gives you a concept called torque, and then you can add up all these torques, both left and right, plus and minus, to get the total torque on the system. And using Huygens principles and Huygens concepts for radial and tangential velocity, you can calculate the angular rotation speeds in terms of radians per second and the angular accelerations in terms of radians per second squared. We'll just skip this. This is a 3/4 stack. You also have beams and masses out on the end. These simulate models of airplane wings or cantilevers with masses on the end. And again, we use these energy Lagrangians where we don't always sum the forces. Sometimes we'll just sum the energy levels as potential energy and kinetic energy, and then do the force times distance, which is the torque, and we can get various values that we're looking for. And actually, as I said before, calculate the number of photons that cause this phenomenon, how many photons that are monochromed at 200 centimeters per second are colliding with the mass. That's a frequency. We don't need a wavelength. We just need frequency to be able to calculate that. And that frequency is our angular spin velocity of the photon. And if it's monochrome, it exists at one energy value. It's quantized, and it comes out of the electron always at the same monochrome frequency or color in this case. This is a pendulum or a two-force system, again with calculations and torque rotations. You can get into very interesting nonlinear sets of equations and nonlinear mathematics. When you have more than one particle, you get two-body particle motion, and that becomes a whole different science, a whole different set of mathematics, nonlinear calculations. Inelastic collisions are a consequence where energy is not conserved. Conservation of energy is a principle of Newtonian physics. The energy, again, is the energy Lagrangian, is 1/2 the mass times the velocity squared, is equal to the sum of the masses times the height that the pendulum moves through. So you've got potential energy there on the right, both potential energy at the top minus the potential energy at the bottom, and that's equal to the kinetic energy on the left, 1/2 the mass times the velocity squared, final. And again, that's an energy Lagrangian, and we can calculate the number of photons that it takes to create that by adding on the further left of the equation the Planck's constant that we had before, where the sum of those Lagrangian energies are super summed up to modern Newtonian measurable values from Planck scale quantum interactions of the photon quantum interacting with the molecules and masses in those objects, and the mass quantum interacting with the molecules, electrons and protons in those masses to create gravity phenomenon and to create inertia phenomenon from the photons causing motion. So on the left-hand side, that would be Planck's Lagrangian equation that we've added to this theory, where the sum of the energies on the left-hand side is equal to h dot times the angular spin velocity nu plus or minus g dot, the gravitational equivalent Planck's constant, times omega, which is the angular spin velocity of the mass quantum particle. And the numbers of those can be calculated until you determine the number of photon quantum and the number of mass quantum that it takes to equal the exact same energy, potential energy minus kinetic energy minus potential energy on the right, and get the exact same number. Inelastic collisions are where energy is not conserved. Again, this can happen from solar interactions and losses and heat losses and energy losses. And just to demonstrate this, we have an object that's rotated a certain distance through a certain acceleration, a certain angular spin velocity, and a linear transformation at the same time of 1,000 meters per second. And we give its mass and we give its momentum. Momentum is equal to the mass times the velocity. Delta P is the momentum. And that is the sum of the masses, again, times the velocity is the momentum. And then we come down here and get the energy Lagrangian again, which is 1/2 mv squared plus 1/2 k times x1 minus x2. This is an elastic constant. And hang on one second. So that's a spring constant, k, plus 1/2 I omega squared, which is the moment of inertia, times the angular velocity squared, which is another energy Lagrangian value for kinetic, angular kinetic energy. Sum all the masses times g times the height that it's moved. And then we've got this equivalent heat concept, mass times the the equivalent heat value for C sub P times the temperature final minus the temperature initial. That's another energy Lagrangian where you've got heat from the sun involved, heat losses and heat gains, where you've got constant volume and constant pressure. This is the constant pressure value for heat coefficient. Then we got a mass spring system, which is very common analysis. Basically sum of the forces again. We divide those into vectors. We subtract the static forces, the static frictions, and we end up with, again, an energy Lagrangian, if we wish to, where it's kinetic energy 1/2 mass of the velocity, plus the F1 times h, which is work that's done through the system, force times distance, and then force times the sine of the alpha of h, which is, again, a work that's done on the other system, minus the potential energy that it travels through, mass times gravity, and then force times h again, which is another measurement of the work done. And then we can add in any spring constants we have, if they're there, k times the spring the spring differential in terms of the distances that it's been moved, and add any of these other terms on the right hand side. Force of friction, which would be the normal coefficient of friction, or the static coefficient of friction, times the normal force. And those are all Newtonian based Lagrangian concepts that supersum to our Planck scale concepts. The rest of it is Newtonian fluids and concepts, where we calculate buoyancies, forces, and displacement. Basically, we'll do this in another lecture later, because buoyancy is more interesting. And I think we'll end this lecture at this point for Newtonian forces, and talk about elastic limits in another lecture, and calculating and heat transfer and energies and entropies. All this is suitable for another lecture series later. So I hope you enjoyed it.